So computer versus the brain, they both send electrical signals to send messages. They both transfer information, but the computer transfers much faster than the brain. We also had a look yesterday at the optic nerve, which is what transports the electrical signals from your eye to your brain to help you see things. And that's what we learned when we were looking at lenses. But what I want to show you guys today is actually some binary code, some very, very basic binary code. I'm going to turn the microphones on and I want you guys to read what's on this screen. Computers transfer information in
Bits and binary code.
Bits and bytes are the units of computer processing, much like if we're talking about distance, millimeters, centimeters, meters, and kilometers. We're going to talk about bits and bytes and binary code. Now, I want to show you guys a bit of a video to explain how to read binary code. We're talking about binary code, which is how a computer is able to transfer information to itself. We're going to use bits and the slightly larger unit of bytes. We've had a look at binary code already, and we know that it's only made up of ones and zeros. And so to help kind of explain it better, we're going to stick with the light bulb analogy, and then we'll have a little maths puzzle at the end. So if you've got a light bulb, if it's on, if your bit is on, then it means it's got a value of 1. And if your light bulb bit is off, then it's got 0. Like 10 millimeters is 1 centimeter. 8 bits is equal to 1 byte. We had a look at Super Mario. We had an 8-bit Mario. It was very, very blocky, like a Lego man. And then we had a 64-bit Mario, which had a lot more detail. And that just means that the 64-bit Mario had more units of processing power that went into making it. As you go across, you read it from right to left, and if the first light bulb bit is 1, the next one is double that, which is 2, the next one is double that, which is 4, the next one is double that, which is 8. So if each light bulb bit is double the last one, what would the next light bulb be? What value would it have? If I was going to put something here,
16.
It would be 16. Good girl. And then if the 5th light bulb was 16, what would the next light bulb be if it's double? 32? Yeah, 32. And so if that's 32, what would the next one be?
The next one will be...
What's double 32? 64. But yeah. Yeah, that's right. Yep, Amy got it. She's telling us the sign language. Cool. Okay, so now this guy is going to show us how to make numbers. Okay, and we're only going to do some basic numbers, but it's kind of like a maths puzzle. Let's say that you've got different card values, and to make a number, you can only use each card value once. Okay, let's have a little look. Basically, to show 0, you've got 0, 0, 0, 0, because you've got no 8 values, you've got no 4 values, you've got no 2s, and you've got no 1s. We're going to count to 5. Okay, so if we want the value of 1 in green, then we just need to use one of the 1 values, okay? You can only ever use 1. You've only got 1 of each value available, so you can't have 0, 0, 0, 2. It's only in 0s and 1s. How do you think we could make a value of 3?
We take 1 multiply 2.
Yeah.
And
plus, so we need a value of 1 to get from 2 to 3. So do we need to use any of the 8 values?
No.
Nope, no 8s. Do we need to use any 4s? Nope, 4 is too big. Got 1, 2, and then what else do we need to make 3? We need a 1 value?
1. Yes.
Yeah, that would make 3. It's basically 2 plus 1. So 0, 0, 1, 1 is 2 plus 1. We don't need to build 4 from any of the other blocks because we've already got a value for 4. That's our 3rd digit here. So we've got 0. We don't have any 8 values because we don't need them. We've got 1 4 value. And then we don't have any 2s, so we put a 0 in it. And we don't need any 1 values, so we put a 0 in there. So 0, 1, 0, 0 is equal to 4. How can we make 5? We need 4 plus 1. Good. So we put a 1 in here. Then we had 0, 1, 0, 1 is basically 4 plus 1, which is 5. Bits and bytes. A bit is the smallest piece of information in computing and digital communication. For example, in distance, it would be 1 millimeter. Time would be 1 millisecond. And computing is 1 bit. It's the smallest bit. If you've got 8 bits, that equals 1 byte, the same way that 10 millimeters equals a centimeter, like I said before. We're going to use the light bulb analogy. And I want to do this. Okay, so we're going to do a little bit of a quick maths puzzle just for a couple of minutes and then we're finished. Now, if I have this as my binary code, 0, 0, 0, 1. What does this binary, what number does this represent?
8421.
8421. Well, we've got, do we have any 8s? We've got 0 8s. Do we have any 4s?
0. No.
0 4s. We don't have any 4s. Do we have any 2s?
No.
No, we've got 0 2s. And do we have a 1 value? Okay, good. So if we've only got 1 value, what number is that equal to?
1.
1, exactly. So this is the maths version. We've got 0 8s plus 0 4s plus 0 2s plus 1 times 1, which is 1. Okay, so a little bit of binary code here is 0 0 1 1. What number does that represent?
3.
3, good girl. So do we have any 8s?
No.
Nope. Do we have any 4s?
No.
Nope. Do we have a 2?
Yes.
Yes. And do we have a 1?
Yes.
Wonderful. So yes, Amy's quite right. 1 times 2 is 2 plus 1 times 1 is 1. 2 plus 1 is 3. Okay. And last one before the puzzle bit. What does the binary code represent here? Do we have any 8 values?
Yep.
Yep. So we've got 1 8 plus, do we have any 4s?
Yes.
Yep.
So that means it's 15.
Good job. That's exactly right. So we've got 1 8 and 1 4 and 1 2 and 1 1, which adds up into 15. Now, this is the maths puzzle. So this is a byte. This is 8 bits. Each one, you read it from right to left, and each value is double the last one. You can only use each light bulb or bit once per turn. That means you can only use 1s and 0s. Any light bulbs you don't use must have a 0 in them. And I want to see, how can we make the number 12 out of these card values? We can't use 16 because it's too big, but how can we make 12 out of what we've got?
8 and 4.
Yeah, so we put a 1 here and a 1 here. So that's 8 plus 4. And if we're not using the other values, what do we write in them?
0.
Yeah, so 0. Next number is 40.
You make 40, right?
32 and 8.
Good
Good job.
And then what
And
do we
what
put in the other values if we're not using them?
0.
0.
Exactly.
Right, and the last one. How can we make 43? So we just got to 40 with Bill by using 32 and 8. How can we add 3 more?
2 and 1.
2 and 1. Okay, so we're going to fill into my light bulbs.
32, 8, 2 and 1.
Good job. 2 and 1. And then what do I write in the other light bulbs?
0.
0, 0. What is the binary code for 43? Read it from left.
0, 0, 1, 0, 1, 0, 1, 1.
Perfect. And just like that, you guys can read some basic binary code. Cool. Okay, so that was how computers talk to themselves. Like I said, I promise that now that we've had a look at that, we'll move on to something else. But thank you very much. And in the next class, we're going to look at more wireless ways or other ways that information can be transferred from place to place.